Hi everyone, welcome back to another UCLR video tutorial. This time we'll be doing a deep dive on the design process of my third year project, which was creating carbon fibre wheels for the Eco Marathon car. So this is not going to cover the background and the justification on the project. For that you can see my dissertation, which should be available in Microsoft Teams if you're part of UCL Racing. Otherwise, this video and other bits of documentation on my project are going to be made available on my website at theobound.com/carbonwheels. So hopefully by the time this video is up, that website will be up. I'm still working on it, and alongside that, other bits of documentation that I'll be making over the next few weeks. So with that said, let's get started. So the first thing I want to look at is the overall design process as is outlined in my thesis. And this was developed partly from my own experience with projects like brake pedal for the car in the past, and also big thanks due to ETH Zurich, their Eco Marathon team, who have really written the Bible on Eco Marathon car development. So we start out with a minimum viable product, which is essentially just making a very simple design which covers the basics of what we're trying to achieve, and not much more than that. And then we go to simulations, which will let us improve and iterate on that initial design. And part of these simulations is shape optimization, which you may be familiar with from some of your scenarios you might have done in second year. So we're going to be using a topology optimization tool to take the initial very simple shape of the wheel and figure out the ideal shape to maximize performance. Having conducted all those simulations and refined the design, you then validate the design, just putting it back through FEA simulations again to evaluate the structural integrity of the wheel. And finally, we're going to be looking at defining the carbon layups. This is one of the more complicated bits, but it's not too difficult to learn because Ansys is so well documented. So we're going to be looking at Ansys ACP Composite Prep Post, which is Ansys's tool built into Workbench and Ansys Mechanical, where you define the layups. You have a pre-stage where you do all of the pre-work in terms of defining the layups, and then a post-stage examining the results after you apply your loads. Right, so with that said, let's jump into the minimum viable product, and that is this very simple wheel model I made in Fusion. It can be made in any CAD program really. We're going to export it to Ansys, but since we're familiar with Fusion, might as well use that. One more thing I should note before we go into this, that design process I just covered from my thesis is reflected here in Ansys Workbench, where we outline the structure of our analyses. It may look confusing for now, it probably does, don't worry about that, but essentially we come up with a minimum viable product, we run it through some simulations, we optimize it here with structural optimization, we get the optimized geometry, and then we feed that optimized geometry back into a design validation process. Once we do that, we can move over to another Workbench system. This will also look incredibly complicated, but it's more simple than it looks. Here we take the geometry we refined from those initial simulations and we define them using ACP Pre, where we can tell Ansys how we want the different layers of carbon fibre to be. And then we run more static structural simulations, validate how they perform under load. Right, back to Fusion, the minimum viable product. So, to tell you a bit about what you're looking at, we've got two components. We've got a rim, rather the wheel itself, and we've got the hub. So I'm going to hide the wheel, and this is the very simple wheel hub I designed. And to give you some context on what you're looking at, this is a cross-section of the Hope Pro hub that the team has been using on the wheels for the past several years. It's a pretty high-end hub from what I understand. It's fairly lightweight. It's meant for racing bikes. So essentially the way a hub works is it permits movement of the wheel with as little friction as possible. So you'll have an axle going through the hub, and we have these two hub caps here. So this green one and that orange one, those two are separate from the hub. So maybe more clear if I show you here, but this is a separate piece that is external to the hub. And so the axle in the car remains stationary. It slots through the hub, goes through the hub caps, and then it's clamped together. And what that's doing is it is holding the hubcap assembly in place. So just to make that clear, I'll highlight the components that are being held in place. So the outer cap, the inner cap, the axle, which I don't have in this assembly, and yeah, the spacer, and of course the inner races on these bearings. Those are all held stationary, and the bearings interface with those stationary components to allow the hub body to rotate around the axle. Now, normally on a spoked wheel, if I could, yeah, I don't have the initial spoked wheel assembly here, but you can imagine traditionally with standard spoked bike wheels, you've got the tyre on the outside with the rim, and then there are spokes which attach that rim to the hub body here, and therefore it rotates with the hub body. Right, so I have taken the Hope hub, and since we're going to be manufacturing it ourselves, I just wanted to make it as simple as possible to manufacture. So you'll see I've removed a lot of the complexities from the model. It is functionally the same, and I've tried to thin out the model as much as possible within the tolerances we're capable of manufacturing within, and to minimize weight. So that's what you're looking at there. Next, we've got the wheel itself. So I told you the wheel interfaces with the hub, so compared to spoked wheels, this time with a carbon disc wheel, instead of being attached by spokes, the carbon is simply bonded to the hub body. And this wheel, so I've created following a few different requirements which are all outlined in my thesis, but essentially, let me find this for you. You can find, yes, the rim profiles. Different tyres require different rim profiles. So this is simply the rim profile for the tyres that we use. There are 3 different tyres for Eco Marathon. The tyres we're using, forget the exact number, it's the model number, it's somewhere here, require this crochet rim profile. That is from the European Tyre Standards Manual, which will also be on Teams. And yes, here we are. Those are all the numbers, dimensions. So I've simply taken a screenshot of this profile, put it in Fusion as a canvas, and then sketched around it following those dimensions. Now, I told you this will be a minimum viable product design, in that we're going to use the simulations to optimize that initial design by actually removing material around the wheel. So that is the way a structural optimization algorithm works. It starts with a blank billet, you could call it, the design that occupies the maximum possible volume that you could ever conceive the wheel occupying. Now, this wheel, you're probably thinking, does not reflect that because it's got relatively thin walls, it's got a big hole in it. These walls are at an angle as well. So if you're wanting to remove material, you want something occupying the most volume. In this case, that would be a wheel going pretty much straight down from the widest part of the rim and not really having a hole in it. And the reason I'm showing you this and not what I'm describing there is because those files I have are on a computer I don't have access to at the moment, so you'll have to bear with me on that. However, all the analyses I'm talking about apply to this model, so effectively it should all be the same processes, just for a slightly different model. Right, now we can move on to Ansys. So right, now we can move on to Ansys. So just to recap, we have made that minimum viable product, and now we're going to perform our initial simulations on it. So, right, and you're probably rightly wondering, how did I come up with all of these systems? How do I know how they link together like this? And that is all thanks to the Ansys manual. So in a previous video I covered how to gain access to the full Ansys documentation, and genuinely this has been the greatest resource for my project. All of the Ansys programs are so well documented. You know, if you print this out, it's about 3,000 pages, and it's taught really well from assuming the reader has just a very, very superficial understanding. Now, if you go to the table of contents, you can see analysis types, and you know, there'll be an overview telling you about this, and then I'm thinking, okay, we want to structurally optimize the wheel. I know that from previous experience, not with Ansys necessarily, just with this workflow. And this tells you everything about how to set that up in Ansys Mechanical. And what I want to show you here is the optimization workflow. And here it describes perfectly how to create this system. So just to show you, so I'll just show you how we create a system like that. So first you want you want static structural. So I'm going to make a new standalone system here. Now, static structural is the simple FEA analysis you're probably used to doing from your different modules in second year, maybe first year as well. Essentially, that's inputting loads on a model, and it gives you results on deformation and on stresses, strains, all of that. Now, we can actually take static structural and connect it to another analysis, such as structural optimization. Now, when I'll click and drag it'll highlight these cells here. I want to drop it on the solution tab right there. And that way the results of my initial static structural analysis are being fed into the structural optimization. Now actually, one more thing I want to do before I insert static structural is I'm going to drag and drop a modal analysis. Now truthfully, I don't entirely understand the theory behind modal analysis. It has to do with vibrations and dampening, which those results may not be terribly important for the sakes of our analysis, where we just want to make sure, with a static structural test that it withstands loads sufficiently. However, Ansys in the manual actually describes, somewhere in the manual, it describes that the structural optimization algorithms perform best when they're given more data, and it specifically recommends a modal analysis. So now, when I take the structural optimization, drop it on modal, this is getting data from both a modal analysis as well as the static analysis. So static structural, we define everything here, we get solutions, those all feed into modal, so I don't have to change the setup at all, I pretty much just need to click run. That solves, gives us our modal results, tells us about the dampening properties of the wheel, then we feed that into structural optimization. So that is an overview of what we're doing. So now I'll just explain exactly how we set up all of those analyses. Right. Now the first thing we want to do is, so I showed you our wheel assembly here, and you'll notice it's only a half wheel, and that is because we can actually reduce the computational load required from Ansys because of symmetry. So the wheel is symmetrical, all of the loads are symmetrical in the vertical plane. And right, so typically you can, what I've done here is I've dragged and dropped a geometry block, yeah, one of these, put that there. But really, if you just start with static structural, that's what I recommend. It'll include a geometry block here. Then if you just double click on that, then you can edit the geometry as if it were its own standalone module, like it is for me. Right, now I'm going to go back to Design Modeler. So right click on your geometry and click Edit in Design Modeler. So Ansys gives you 3 different CAD programs to choose from. SpaceClaim, that's seemingly the most full-featured and most recently updated one. I really like it. I actually ended up using it in place of Fusion. Design Modeler is a bit of an older one, seems to have a couple more tools that are useful just for preparing your model for simulation rather than creating designs. Discovery, stay away from that. It's their new software, it's not terribly useful. And you'll enter here and it will look empty. Now, whenever something looks like it's missing data, you'll often see in the tree outline on the left that there's a little lightning bolt, which means we need to generate our data. So I click that, and hopefully it didn't just crash. Okay, great, it didn't. Nice. Excellent. And we are only going to use Design Modeler to do one thing, and that is to define symmetry. So, way we're going to do that is wait for my connection. Right. way we're going to do that is, let's see if I can remember this, I believe it's under Tools, yep, click Symmetry. Now if we highlight Symmetry, it'll give us some details here, and it's asking for a symmetry plane. So just a flat surface on which symmetry is going to exist, and of course for us that's here. And I don't know why it's not letting me select. I think my data might be read-only because the file is a bit broken. Okay, it's because I've already defined symmetry. So essentially you'll click here, you'll click on yellow in any of the details boxes, means there's missing data. So you want to click there and then you select a face. And once you do that, you'll need to click generate again to create your symmetry. And then you'll know the symmetry has been created when this symmetry box shows up under the tree outline, and it'll also create a plane, I believe. Anyway, we've got our symmetry, you know that from that bit in the tree outline. So we can now close out Design Modeler. Now, the next thing we need to do is actually define our material data. So I'll also just go over how these different analyses work in terms of the different building blocks they have. So static structural, when you drop it, that first block is just a title. Then we have number 2, engineering data. That is where you define your materials. Next there's geometry, which we just looked at. Number 4 is model, that's creating your mesh, the finite elements that are used in FEA analysis. Setup, applying your loads. Solution, the calculated solution, how your model behaves under load. And then results, where you can do some post-processing, collect some specific numbers and visualizations of your solution. So I'll double click on engineering data, and that opens here. Now, if I'm thinking about the materials I'm working with, if I go back to the Fusion model, so we've got carbon fibre on the rim, and we've got aluminium on the hub. And we also have a brake disc, and that will also be carbon fibre. Now, I'm actually, for the purposes of demonstration, I'm just going to go to this blank static structural module. This is what you'll start out with, just structural steel. Now if we want to add some materials, I'll click on engineering data sources. Then if we just drop that down a bit, here we've got all of the different material libraries that are within Ansys. So first of all, I'm going to look at composite materials. That opens here, and I should talk a bit about performing simulations on composite materials such as carbon fibre. The material behaviour of composites is far more complicated than for linear elastic materials that you're used to working with, like aluminium, like steel, any of the stuff we normally do in Fusion. And the structural properties of carbon fibre are highly specific on the layups. So each layup will have the individual strands called toes of carbon fibre, the individual toes in different directions. So we can have unidirectional carbon fibre where all of the strands are aligned in the same direction, giving you excellent strength in this direction but poor strength in that direction. You can have woven carbon fibre which has overlapping strands, typically at 45 degrees with each other, and that gives you nice and even resistance in two directions. However, not as strong resistance as the unidirectional material in the longitudinal direction. And then it's not just about the orientations, but also how you layer the different layups of carbon fibre. So you could have one layer of unidirectional, you could have one layer of woven, and then a layer of unidirectional, and then another layer of woven on top of that, and that is going to behave far differently to if we just had 3 layers of woven. So for now, this composite simulation has to be taken with a massive grain of salt. However, that's fine, as we're just looking to do what's called black metal analysis. Super simple analysis where you treat the composite part of the assembly as if it's any normal linear material. And that just allows us to perform the initial topology optimization, get that ideal wheel profile before we then apply the proper carbon fibre layups. So yes. So apologies if I'm rambling a bit, but for now we want to select the most sort of universally representative carbon fibre material that is within Ansys. So we want to go with a woven carbon fibre because that's going to give us somewhat uniform structural properties in terms of being strong in all directions and not particularly strong in any direction. So it should be kind of a worst case scenario really, because an optimized composite design should have some unidirectional layups. So let's see, we want a woven one, and yeah, any of these ones that are labelled woven will do. Now we want to go with a pre-preg, so that just means the layups are pre-laminated. They've got the epoxy already on them, so it's far simpler to manufacture. That's what we use in MechSpace. You can have wet layups where you get just dry carbon fibre plies, and then you have to apply the epoxy yourself. So let's go with a pre-preg. I'll take this 230 gigapascal one, and I'll click the plus. That is going to add it to our materials. Yep, so I just clicked off engineering data sources there. Now we have carbon woven pre-preg. I'm going to delete structural steel because we don't actually have any steel. Right, lastly we want to add aluminium, and that will be under general materials perhaps. Yeah, aluminium alloy. And if I click off there, you'll see, yeah, we've got it, and down here are all of the properties. Another thing to mention, you can create your own materials. You can drag and drop the different properties here. So see what I want to add. Right, I think something's going on with my license that isn't letting me fully interact with everything, but that's okay. I'll show you what I did with my materials. So my analysis, I actually ended up taking the standard aluminium alloy that's from Ansys, I duplicated it, and then I just changed some of the structural properties here, because these are, I believe these are the alloys of aluminium that we actually use in MechSpace. Just wait for my connection to resume. Apologies. Okay, that's how you define your engineering data, your materials. Next, we want to define our model. So double click on this, it'll take you to this, which is the standard Ansys Mechanical screen. Now, simplest way to go through the model is really just going down the tree outline, which will step by step cover what we're looking at. So we arrive at the project. A couple things I'd do. First of all, change the settings here so that you are saving the project before and after solution, because it's not too unlikely that Ansys will crash at some point and you don't want to lose your data. Right, next, look at geometry imports, and lovely, this is what we have imported from that geometry module I showed you earlier. Nothing we can really do there. Geometry right here, we want to define our materials. So we've got the rotor and the wheel highlighted in green. Those are both carbon, so I'm going to go down to material, click on assignment, it'll open this nice window for us, and here are all of the materials I added in the engineering data module. So I'm going to pick carbon fibre. Sorry, I want the pre-preg woven, of course. Apologies again, having to do this remotely. Right, and then lastly, the hub body, same thing. Go to materials and pick aluminium. Great. You can see other things. There's not much really you can change here. It'll just tell you the properties if you want to get the volume or the mass. You can have a look at that there. Right. Okay, now this is where you'll be doing some work. So this wheel assembly, it's designed to reflect what I've done in Fusion, which is following this relatively intricate curve that is defined by the European Tyre Organization. However, intricacies like that are not particularly friendly to simulations. So we want to simplify our geometry as much as possible. And Ansys has a tool called virtual topology that lets you retain all of the actual geometrical properties of your design. However, in the simulation, it will combine some of these faces so that we're not having, you know, too many edges around the model that are overly complicating things. And really, the complication comes from when Ansys goes to make a mesh. So we're doing finite element analysis. So to create those finite elements, you've probably been taught, the wheel is broken down into a mesh, which are those finite elements. And I'll tell you about all of the settings that I went through to make this mesh. But here you can see all of the different finite elements. And I have had to apply some virtual topology to merge some faces so that we're not having excess edges. You can see this edge here along the curve my mouse is following. That is a boundary for all of the different elements. So you can imagine then if we had another two faces there, two edges which are not necessarily needed, then we could get far more elements that are needed, and the more elements you have in your model, the more time it's going to take to solve, and eventually you'll reach a model that requires so much memory RAM that your computer will actually just refuse to run the simulation. So we want to avoid that. So virtual topology, all of these colored faces are where virtual topology is applied. And I'm actually going to delete the virtual cells. I'll go through this with you on how we apply virtual topology. In fact, I'll delete the whole thing. So it's not a very obvious thing within Ansys, but if you right-click on Model, click Insert, and we're going to click on Virtual Topology. And then so Ansys has a context menu up in the menu bar here. So something I should probably also go through, different menus. Got Home, that allows you to solve, define your units, simple global things like that. Display, change your views, change, what the appearance of your model. If you you want to make your computer run a bit faster or want to see the exact curves a bit easier, you can do that. So here we have the virtual topology menu, and I get that by clicking on our model, on our item there, and clicking there. Right. Now you'll see all the options here are grayed out. It's not the most intuitive thing, but right, I'll show you here. So here are some edges that we actually want to get rid of, because again, unnecessary complications for the meshing algorithm. So I'm going to select those three faces there, and I'm going to click on Merge Cells. Right, and you'll see it's actually created a virtually merged face, which is great. Another thing I can do, that edge, probably not entirely necessary. Let's see if we can merge those. Sometimes Ansys will refuse to merge for you, but good, that worked well. And then lastly, let's do that here as well. Great. So that's working really nicely. Another thing you might want to do, if you want specific control over the different sections of your mesh, so when you're defining your mesh, I'll show you that now. When we're defining our mesh, if we expand mesh here, you'll see there are several different components here, and you'll see I've called them small components, rim, inside faces. So on different parts of the model, I am applying differently sized elements. And we are only able to do that on distinct faces of the model. We can't sort of mouse select an area that we want to apply that to. So let me give you an example. Right, so the rim profile here. So I actually wanted to have smaller elements on just this part of the rim here. So the walls here, I want them to be separate. So I need to create an edge here and an edge there. And we can do that through virtual topology. Right, you rejoin me a couple days later in a different flat in a different part of the country, and hopefully somewhere where the sun will not be glaring directly into my eyes, so I won't be squinting as I do the rest of this. So back to defining the virtual topology. So I want to define these edges here. The way I'm going to do that is I click on the virtual topology item in the tree menu, and then we want to, so we've got a few options here. We can split edges. So what I'm going to do is, with this menu bar here, I can choose what my cursor is going to select. So I want to go to select vertices. And if I control select, so I can select multiple things at once, and then I can click split face at vertices, And there we are, got a new virtual edge right there. And I'll repeat that here. And split the face. And then now you'll see if I go to a face selection, I can now select these two faces separate to that one, which is great. That means we can, if we wanted to apply a mesh sizing option just to this face, we can. And I'll show you how we'll do that now. So what I do here, normally when you start out with a mesh, and I'll just remove all of these. So when you start out with your project, you'll just have mesh like that. It won't have any items under it here. And you'll see we've got, and you'll see we've got a few options here, but these are global options, which mean they apply to the whole mesh, which isn't always efficient. So I'm going to insert a sizing option. And then it's going to ask for geometry. Now we can either select by just selecting individual faces, so we want these faces to all have a certain size, or we can also do a named selection. And that's really handy if you're repeating a lot of selections throughout the course of this project, which chances are you will be doing. So to create a named selection, we can go to name selections, insert name selection, and then we can pick some faces. And because that's what I last selected, that's what it's given me, but I'm just going to pick, so we clear the selection. I think I just have to click out and then back in. Yep, click apply, then we got one face there, and we can call this, we rename or just press F2 on your keyboard. I'll name that rim face. Great. And then if I want to set the sizing just for that face, I can go to name selections, I can pick rim face. Lovely. And then that is no longer yellow because we've fully defined it. Then we've got a few other options. So element size, we can change that. Your cursor will actually show you this radius here that's following my cursor is the size of the element. So right now it's at the default, which is 8mm, and you'll see that's really quite large. Now, when sizing mesh elements, you want the elements to at least have 2 elements in each dimension. So say in this dimension, which is the X dimension, you know, we want this to be split into 2 across. Right now, 1 element is actually going to be too big to even fit there. So we could, let's try 3mm. And then you'll see, looks fairly good. Yeah, we'll get 2 elements there just to be safe. Put it down to 2.5 maybe, and yeah, that should definitely be good enough. However, you'll notice we're not really going to capture these details here at the curvature because this element is larger than that actual radius. However, we've got a few options here. We've got capture curvature and capture proximity. When both of these are set to no, your mesh will have a uniform size, meaning in any given selection, all elements will be the same size. You'll get a very simple mesh, which is good as it saves some computational complexity. However, it may not always capture the shape of the object accurately, as we see here. So if we enable capture curvature, it's going to see these bits where we've got more extreme changes in geometry, and it's going to insert a greater number of nodes there, and with more nodes means more intersecting mesh edges, more elements overall. Another thing you can do is capture proximity. That has to do with how close the edges are to one another, I believe. So here, we've got this edge is far closer to this edge compared to here, where the edges are further apart, and therefore it'll create more elements here. We can create both there, and really, there's no one set rule about how to do all of this. Essentially, you have to just play with the options, look at the troubleshooting messages that will inevitably pop up, see what they're suggesting about your model, look at how long it's taking to generate a mesh, if it's getting caught up on a certain part of the mesh, and that may highlight that you're doing something inefficient in a certain area. So that all, I'm sure, sounds quite abstract now. I'll give you some examples later on of the troubleshooting steps I had to take to refine the settings in my mesh. So yes, we've pretty much gone over the relevant options on the sizing sub option in the mesh. In the global section, we've got a few more options, and again, I would go in and create another sizing one, and maybe all of the rim surfaces we want to be a certain size, because that's where all the loads are. We'll need more detail there probably, because there's greater deformation. Here, really simple flat surfaces, which do not take so much of the load. We can save on computational resources and just select these big faces and put those up to a mesh size of 5mm maybe, because we don't need to capture so much detail there. So that's the sort of stuff you would do with the sizing. Now if we go back to the global options, I'll just run through what you have to play with here. So display style, that's just, I don't think that's too important. Physics preference is one to pay attention to. Now the Ansys manual will tell you in detail about which physics preference you should be using for your analysis. What this does is it just tweaks the meshing algorithm, so I believe not just how it generates the mesh, but also what it defines as an acceptable quality of mesh. We'll get to mesh quality in a minute, but yeah, that's something to consider, and the Ansys manual, of course, has all the detail on this. So let's go have a quick look at that section of the manual. Another pro tip, if you highlight any box in Ansys in one of the menus and press F1 on your keyboard, it'll take you directly to the relevant bit of the manual. So I'll just wait for that to load. Great, and here we are. And again, you can see all of the options in detail and what they do. So we want to look at, what are we looking at? Physics. So defaults, physics preference, and yeah, here it goes into detail on all of the different options and which you should choose and what is different about all of the options. For the purpose of UCLR, I think you're going to be looking at mostly mechanical or nonlinear mechanical, and then CFD if you're doing Ansys Fluent. But for the purposes of this tutorial, which are on Ansys Mechanical, the only two you'll really be considering are mechanical and nonlinear mechanical. and this has to do with elastic theory and linearity of the assumption of linear plastic behavior in different materials. So this actually depends on what sort of analysis you're doing. So you don't need to understand all of plastic theory for this. However, I'll just quickly go over just give you a brief explanation on that. Right, so there are, 5 assumptions of linear elastic theory. 1, continuity, because this is, right, so without going too much into detail on elastic theory, there are the 5 assumptions. So continuity, the model is a continuous material. It's divided into finite elements. So this assumption is made with finite element theory. Homogeneity, so properties must be the same in all sections of the model. Not necessarily true with carbon fiber materials. However, because again we're doing a black metal simple analysis, we can ignore that for now. Isotropy, again, material properties being the same in all directions, not true of composites. Elasticity, the material recovers after a load is removed. Now this and the next assumption of linearity, a linear relationship between stress and strain, these mean that in Ansys, for a linear model, changes in geometry as load is applied are ignored. So that means the way Ansys solves is it applies a load in increments, and with a linear model, it is not calculating how the model deforms after each step. That takes a lot of computational effort. However, Ansys advises that for thin-walled models, where the thickness is less than 10% of the area in the other plane, then you have a non-linear model where Ansys should be calculating the deformation after each load increment. So that was probably a lot to wrap your head around, and clearly I've not even wrapped my head around it fully because I could barely explain that. But for those purposes, we're going to go with nonlinear mechanical rather than linear mechanical. Nonlinear because we've got thin walls, and the deformation under load is going to be too significant to ignore. So in the Ansys manual somewhere, maybe I'll link it, it'll tell you exactly what amount of thickness requires a nonlinear analysis. Excellent. We got the physics preference sorted after much explanation. Element size, typically with the global mesh, I set this to the maximum sized mesh element you want to have anywhere in the model. So for the walls, actually, these look like 8mm. that global mesh size applies there. Then anywhere else in the model where I've got smaller elements, that is coming from individual local mesh sizes. So growth rate and max size I leave at default. Mesh defeaturing, what that does is it's you enter a size, and then if Ansys detects any features in the model that are smaller than what you've entered, it will ignore it in the mesh, and that can be good for removing some complexity, such as here there's a very, very small radius in reality, but it's, if we were to capture that with a mesh, we would need really, really small elements there. It would add a lot of computational complexity. So because I've got the defeature size at 0.04 of a millimeter, it is ignoring that. Again, capture curvature and capture proximity, the same options as before. Typically for global, I leave those off, but for other areas of the model, I might leave it on if there are significant changes in curvature. Okay, these quality, this is a lifesaver. So under check mesh quality, you'll have a few different options. So no, you always want it to be checking for the mesh quality. Basically, Ansys has some predefined limits on what it considers to be an acceptable mesh, and Ansys actually says, I believe, that this can save you from doing a mesh convergence analysis. So in second year, third year as well, I think we're taught for both Ansys and Abacus to do a mesh convergence study. What you do there is you start out with a very granular mesh with large elements, and then we increase the number of elements, decreasing the element size over and over. We'll perform a simulation, gather some results. So, perhaps a graph of deformation of the body through a specific coordinate. And you'll get a plot of how that deformation is measured. So on the x-axis, you've got your number of elements. On the y-axis, you'll have deformation, and then you'll get a curve, and then eventually that curve will plateau at a certain number of elements. That takes a lot of work. It's probably still more accurate than doing Ansys's mesh quality checking, but this can save a lot of time, particularly if you're repeating analyses. Adjusting your model over and over can take a lot of time to have to redo that mesh convergence. So there are a few options. By default, it is on yes, errors and warnings. That means that in the simulation output dialog, it will be telling you in text, and I'll show you, it's not the most, it'll show up in the warning messages here, or it'll show up in solution information. Which I don't have here, but I'll find an example of that later. So, mesh quality worksheet is great. This is a really powerful tool because it gives you the most detailed breakdown on how your mesh is performing. So here we've got the different quality criterion. You don't even really necessarily need to understand all the theory behind these. I certainly don't. What's good though is Ansys has predefined quantitative limits on what defines a good mesh. So target limits, so warnings where you, if a mesh element exceeds this, you may want to look at it, and then an error limit where Ansys will consider the mesh quality insufficient for your analysis. And then you'll see here the number of failed elements, so great for all of these criteria, no failed elements, and then you'll see under warning we've got nearly 1,000 for this criteria, which sounds like quite a lot, 183 here and then 1 here. So I have no failed elements here, so in theory I could send this straight to analysis. However, to be careful, I want to look at the warning elements I've got. And let's see, on the aspect ratio, 0.16% of them are at the warning limit, and the warning limit is 5, and the worst is 18, whereas error is 1,000. So we are, 2 orders of magnitude off from triggering an error, and we haven't exceeded the warning limit by too much. So, I would think that's okay. You can right click. So if you hover, first of all, it'll explain to you, what this criteria is, and then aspect ratio, that's about, I believe that has to do with how much elements are being stretched, whereas ideally they should somewhat conform to the tetrahedral or rectangular shape. So a really high value just means it's really being distorted and it's not going to provide the most accurate analysis. If you right click here, we can then select show warning elements. That then, it looks like it does nothing, but it actually creates a new named selection. It'll be at the bottom. And now if we click on that, it highlights all of the elements in the model where we've got some aspect ratio warnings. And we'll see most of them are actually in the break disk, which is perhaps the most simple bit of the model. So this would be quite easy to solve. The most significant loads are applied elsewhere, so I might okay this, but this just gives you an idea of how to find the elements of your model that might need adjusting. Yeah. Go back to the mesh quality worksheet. What else? Max corner angle we'll also want to look at. Again, it's 0.031. That's really nothing to worry about, honestly. But again, I'll highlight that. And yeah, they're randomly dispersed, so it'd be difficult to sort that out. But again, that's such a small percentage of the model. So I'd ignore that unless when we go to solve we get some errors and error messages highlight something about the mesh, then we might want to look at this. But for now, we can consider our mesh to be adequate. So at that point, once we got our mesh, we'll also want to generate connections. Now, so once we've defined all the mesh options, I should say, go to mesh and we click generate mesh, or you can right click and click generate or update. Then it'll bring you back to connections. Now these you may be familiar from Fusion, where there's the contact tool that automatically detects contacts in your model between the different parts. So I would make sure to double check your contacts here, because it will have automatically made these and we want to make sure that they are accurate. So I'll highlight the first one, contact region 1, and we can see, okay, we've got one contact face and one target face. This is the contact, so each contact will be a pair. It'll have a contact body and a target body. Here we can see that it's highlighted the inner face of the wheel, and that is should be joining to the outer face of the hub, and we can see that. Perfect. No issues with that. Go here and let's see, yep, the brake disc is bonded to the outside of, the outside of the hub. Perfect. And you can define the different contacts. You can have frictionless, rough, frictional. The simplest computationally is bonded. And again, highlight this, click F1, and you can get more details on the different types of contacts there. I've only worked with bonded though. Lastly, you can, on connections, you can insert a contact tool. Now this is something I only discovered after really going through the troubleshooting steps that show up in the solver output. But if we go to the contact tool, and we'll select all contacts and contact side both. So we'll click add and apply, it's got them both. Next, I'll click generate initial contact results. Okay, and so I'm not getting the proper results just because I've kind of broken my model in the process of this tutorial. But when you click generate, it'll give you these results, and any grey or white regions are fine. So white is fine, and then grey means we've chosen to disable a contact. So right, these are only grey because they are duplicates of these two, and that's because every contact is a pair. So if you see greyed ones here that seem to match the white ones, that's fine, ignore that. It's the red, yellow and orange messages you want to look at. So red, the contact status is open, but the type of contact is meant to be closed. So that means perhaps if you've manually defined a contact, which is necessary sometimes, if Ansys does not automatically pick up the contacts, that means essentially that you're defining a contact, but Ansys does not detect that they're touching, which is going to behave weirdly under the simulation, because as the body deforms, it will expect to be in contact with the other body, but it's not. And then orange is similar to that, but there's a bit of a gap between your mesh elements. So check penetration and gap compared to pinball and depth. So pinball is the radius that defines how you detect a contact. So a larger pinball radius means, if you've got a pinball radius of 1 millimeter, that means if we are let me see if I can get a display of it. Okay, so if I'm manually defining a contact, yeah, say I had to manually define the hub and this face. So I'm defining the bond between the hub and the wheel. And we'll say it's bonded, and I can adjust the pinball region here if it's necessary. Program controlled, the automatic option should almost always work. I did have to modify this at some point just because I had a weird mesh where I was really trying to bring down the computational resources needed while still meeting the accuracy requirements. And I met the accuracy requirements, but then the contacts weren't properly picking up, so I had to manually define them. And we can enter a pinball radius, and then when I highlight, no, it's not going to show me that. Okay, yeah. I mean, you can, I don't know if that's the actual size of the pinball, but you can imagine if that's your pinball, it lies on the face of a body, and then if we're within that protruding region from the pinball, if another body is intersecting that red bubble, then it will be detected as a contact. So you can adjust the size of that as needed. I believe that should be all. Yeah, I believe so. Yeah. Okay, and next you'll get to, so you'll have generated the mesh, and then you're ready. Once you've gone through the mesh quality worksheet and everything looks fine, we'll go down to static structural, and here is where we have to define all of our loads and supports. Right. So first thing we'll do is, so when you start out with the static structural model, you'll just have this, you'll have analysis settings, all of these ones with the X there, those won't be there. All of these here also won't be there. So I'll kind of walk you through it as if we're doing it from the start. So if I go to analysis settings, so steps, I mentioned earlier the solver solves iteratively, so it'll break down, even though you've only got one load case or one load step, it will often break that step down into several sub-steps, and that's just because it may have such a large effect on the stresses and deformations going through the body. It won't be accurate unless you break it down further. Typically, I leave the number of steps at 1, so I leave all of these 3 options at 1, and then I'll turn on auto time stepping. And I'll choose to define that by sub-steps rather than time. Effectively, steps correspond to a time. Either one would work, but sub-steps is good. So we'll leave the initial sub-steps at 1 and the minimum subsets at 1. And I like to use a maximum number of sub-steps at 10. Typically, Ansys will figure out how many sub-steps do we actually need to break this load down into, and it will do it between 1 and 10. Typically that's been enough. In the past I've gone up, depending on certain warning messages I've got. This will all become clear once I go through all of the warning messages I've actually gotten. But yeah, 1 and 10, typically good enough. Solver type, so I typically leave that at program controlled. What you can do is go to solution and go up to solution and click on resource prediction, click on analysis environment. This is really helpful. This will also give you a bit of an idea on if you've set up your model efficiently. So let's see, this says right, so we've got 2 solving methods, the direct solver and the iterative solver. The iterative one is typically far more memory efficient, so yeah, halves the RAM usage, more than halves it, and it will be quicker generally. With nonlinear analyses, it sometimes or always has to revert to the direct solver. One thing I was happening was I set it to program controlled, but sometimes the iterative solver will fail, and Ansys will then default to the direct solver, and that's fine. That happens in a lot of analyses. However, if you're getting that over and over, to save solution time, we can just disable the iterative solver, go to the direct solver. Even though it's less efficient, it actually works for some cases. And yep, you can see a time chart here, so depending on the number of cores your PC has, so I've got 8, should be about 2.5 minutes for either solver. That's great. And then memory is more of a concern. So yeah, this is an iterative solver, much less memory, whereas if we go here, if I've got 8 cores, 19 to 41 gigabytes of RAM, I've only got 24, so that might be a risk. You can do simulations that exceed the RAM capacity of your computer. What it does is it uses your hard storage as virtualized RAM. It works fine, but it does run slower. So ideally stick within your RAM requirements. Also, if you really massively exceed your computer's RAM by an order of magnitude, so if I've got the simulation, if it's requiring 80 gigabytes of RAM, there's a chance that the simulation will just refuse to run entirely. So this will give you a good idea of whether you'll have a successful and or efficient simulation. And that's some insight on direct versus iterative solver. Typically, leave it at program controlled. Force it to be direct if the iterative solver keeps failing and it's just wasting time. Large deflection. Now this is actually how you enable a nonlinear analysis. Nonlinear analyses pretty much at least double or sometimes triple the amount of time your simulation will take. Ansys is quite explicit about, in the documentation, it urges you to really enable nonlinear analysis if you've got thin walls like this. It was taking, sometimes several days for these nonlinear analyses to solve for my model. I actually turned this off and then compared the results, and they were fairly similar. So what I do is, if you got a nonlinear model like this, where the walls are very thin and undergoing large deflection, then, I would do one where you've got it on. It could take several days, but, it's important to get accurate results. So I'll do one with it on, and then I'll do one with it off. And the off one will be much quicker, and then I'll compare the results. If they're fairly close, I'll just turn off large deflection, and that's what I did here. And anyway, this is not my final model. Again, this is a black metal analysis. We haven't fully defined all the carbon layups, so I'm going to say it's fine to leave off the nonlinear analysis. So I don't touch any of the other controls there, nor do I here. Restart controls, yeah, leave these on program controlled, just so that if your model does crash as it's solving, you can have some restart points. Nonlinear controls, don't touch that. Again, program controlled, that will be determined by large deflection. That's fine. Store results at, this is something to take a look at. I would typically leave this on last time point. All time points means it is saving results at every single sub-step. If you've got a really large model, your model could end up taking, 100 gigabytes of storage. So I would typically just put this at last time point, unless you need to see the deformation of your body under a period of time. Otherwise, you can do equally spaced points, maybe get 2 or 3 results over the whole time period rather than 10. And file compression, leave that on program controlled. And yep, delete unneeded files, keep that on, otherwise you'll just run out of storage. That's all good for the analysis settings. Now to actually set up the analysis. Right. So fixed supports. Right, so basically you'll need to work out what your supports are. So I've got in my dissertation, I've figured out all of my loads. So yeah, all the load cases are here. Yeah, so we've got the weight of the car, we've got the lateral force going through the tyre, we've got an axial force, so from the, what was that, from the braking, and then tyre pressure. And I believe, not here, but I've got a diagram of those forces somewhere. Here we are. So these are the forces I'm aiming to apply in Ansys. That tyre pressure, that axial moment, which will apply as a force, that lateral force, and then the gravitational force. So I will go back to my PC and let's start with, and also we've got the resistive forces. So if I show all bodies again, we need to prevent rigid body motion in any static analysis. So we're going to click here, insert, and we're going to do fix support. I'm going to fix these two faces. That is because the brake caliper is applying the resistive force there on the brake disc. Next, we need to prevent motion of the wheel in, so when the wheel's on the car, it can move around the axis, however it cannot move side to side, it cannot move up and down. So the way we're going to define that is with a cylindrical support, because this restriction of movement is actually coming from the bearings themselves. So go with a cylindrical support, and then we're going to pick the faces. So I'll go with that face and that face because those are where the bearings are. And it is always, always have to think about the three different orientations. So tangential, axial, and radial. So axial means going through this axis. We don't want that. Radial means moving. So if you can imagine the inside radius of the circle, it'll be moving. Apart from that, not the best explanation. And then axial and radial we want fixed. And it's tangential that will allow to be free. And that is really revolving around that. I think, let me confirm, yes. However, if you just Google radial, axial, tangential, like I've had to do, you'll see the different orientations, so be careful with that. Okay, next we want to do the tyre pressure, so again, insert, pressure, and this is so simple. Just go here on these faces, and I should have a named selection for the rim surface actually. Yep, oops, rim surface, it's broken. Anyway, you get the point. We'll be selecting all of those surfaces, and we want to apply, go back, or whatever. I'll try to keep this brief, because I think we're already approaching 1.5 hours. Sorry about that, if you're still watching, hopefully you are. Put that at 90 megapascals. Nice. Defined by, so you can do normal to, which means it will be acting normal to all the faces, which is a close enough approximation to how the tyre will be applying pressure. ETH Zurich went into more detail about how that pressure was applied. I think normal to will be a kind of worst case scenario, so this is okay for our purposes, but you can define components or in X, Y, and Z, or you can do a vector. And yeah, cool. What else? We've got a moment. So again, we've applied the moment. Again, same process, insert moment, and that moment is acting, on the rim surface. And here I've done it by components. Got vectors or components. You can choose a coordinate system. So if I wanted to make for example, a radial coordinate system where I've actually got the cylindrical coordinates, so I can pick the radial direction, I can do that. Otherwise, X, Y, and Z is fine. This is a global coordinate system, and you'll see if we have a moment in the X direction, it's wrapping around the X axis, going in a circle like that, which is how the wheel is positioned. Great. What else? Remote force. So this is a force applied from a distance. It should preview, but it isn't. And this is a force, the gravitational force and the lateral force. Those are both considered remote forces because they are essentially transferred from the axle, which lies on the bearings, which contact the bearing surfaces. So the faces I'll select here, the bearing faces, and again, pick a coordinate system if you want. So I've got a different coordinate system here, plane 4. Which is one at the center of the wheel. And I know that if I go back to the remote force, I know the distance between the center of the wheel and the center of the car, basically. So it's 500 millimeters in is the axle. So that's what I've done. The X coordinate is 500 mil that way. What else? X component, yep, so again, these are applying to not the global coordinate system, but plane 4. So X is going that way, Y is going that way, and Z is going that way. So X going that way, yep, depending on which side of the car this is, yep. And then the Y component we need to be minus because it's going down. Great. And yeah, that's it. That's about it. And then just click solve. Now, it's probably best if I run through an example of what the solve looks like. But I should have. I should have an example of a finished solve.